Hello again. In this video, we are going to be finishing up our discussion of Unit 13 on second order linear differential equations. You have already seen this page in class, but I am going to talk through it again very quickly, just as a review and to help you pull all of these pieces together. So if you recall, we've been talking about, in this unit, a second order linear differential equation. So those can always be written in this form. A y double prime plus by prime plus cy equals some function g of t. A, b, and c are constant values, real numbers. G of t could be 0, then we call it the homogeneous case, or g of t is non-zero, and then we call it the non-homogeneous case. The general solution is given by y sub h and y sub p. Y sub h is the homogeneous solution, and remember we always write that as a c1 y1 of t plus c2 y2 of t. The y1 and y2 are described down here, so we'll get to that in a minute. This is called the homogeneous solution. It's the solution to the associated homogeneous differential equation, and something that isn't specifically written here is it should say the general solution. So it's not one of those solutions. It's not just y sub 1 or y sub 2. It's the general solution with the integration constant c1 and c2 in there. Yp is the particular solution. So you find one specific solution that works with the non-homogeneous case, and that's your particular solution. So some more details on the homogeneous solution. You find y1 and y2 by assuming your solutions all look like some sort of exponential function. This assumption leads to the characteristic equation ar squared plus br plus c equals 0, and we solve this characteristic equation for the values of r, which leads us to three different cases. The first and easiest case is when we have two real distinct roots, so r1 and r2. This gives us e to the r1t, e to the r2t, so we plug those in, we have our general solution. If we have a repeated root, it's a little bit more complicated, but not too bad. E to the RT is one of our solutions. The other one we have to multiply by t. So t e to the RT gives us our general solution where we take those two and multiply by c1 and c2. Imaginary roots were definitely the most complicated to get to, what y1 and y2 looked like, but as far as you using this, you just simply need to remember what y1 and y2 look like. You don't have to remember all of those details that we did with complex numbers. So for the roots, r equaling alpha plus or minus beta I, that does give you two different roots. You pick up the alpha value and the beta value. These are called the real component and the complex or imaginary component of this complex number. Alpha is the real component, you plug that into the exponential function. Beta is the imaginary component, it's the part that's multiplying by I. You plug that into cosine and sine. So we get the general solution as c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine of beta t. And as I've already said, the order of this does not matter. Same thing up here, same thing up here. The order does not matter because c1 and c2 at this point are arbitrary constants. So you can write them in whatever order you want. But you have to make sure that you do have both pieces and you do have two different constants. Now, for the particular solution, when g of t is not equal to 0, and it's just a combination, a sum, a difference, or a multiplication of polynomials, sines or cosines, and exponentials, then we can use the method of undetermined coefficients to pick what we pick an educated guess, essentially, at what the particular solution would look like. If we have just a constant value, then our particular solution just needs to be a constant. If we have a constant times a polynomial, so an nth degree polynomial, what we're actually going to do is pick a polynomial with all of the degrees. And the reason for that is because the derivative of t to the n involves t to the n minus 1. And the derivative of t to the n minus 1 involves t to the n. And the derivative of, t to the n minus 2. And the derivative of t to the n minus 2 involves t to the n minus 3, and so on and so forth until you get all the way down to t to the 0, which is just a constant. So we have to possibly consider all of these values. So that means if you have a t to the 10th power on your right-hand side, you are going to have 10 undetermined coefficients that are multiplying t to the 10th and t to the 9th and t to the 8th and all the way down to t to the 1st, and then t to the 0, which is just a constant. Okay? In the case when the right-hand side is an exponential function, then the right-hand side is that same exponential function. If we have a cosine or a sine, we have to have both cosine and sine in our particular solution. If we have an exponential multiplying a cosine, then we have to have, or an exponential multiplying a sine, then we have to have both the exponential multiplying the cosine and the exponential multiplying the sine. But your arguments for the cosine and sine and the arguments for the exponential, you choose from what is in your right-hand side. Now there is a note here. If the YP that you pick would be identical to the corresponding homogeneous solution, then you need to multiply YP by T and try that to see if it works. So that's what we did in the previous video for this problem, because cosine 5t and sine 5t were our homogeneous solution. So we multiplied by a t. If the corresponding part of the homogeneous solution is a repeated root, then you need to multiply yp by t squared. And the reason for that is if you have a repeated root, you have already multiplied something by 1t. So you need to make your particular solution distinct from both of these pieces. So you're going to multiply by a t squared. Okay? Now remember that you can add and subtract particular solutions if there are multiple terms that are added or subtracted in g of t. So this means that you can either do it when you are finding your form. You can just have a whole bunch of pieces added together, and we'll see that in this next problem. Or you can do what you have already seen previously in this unit, which is if you already have your two particular solutions, then you take them and you add them together appropriately. And remember, this does mean a linear combination, okay? So if you have something like k1 g of t plus k2 g of t, let's say h of t, and you have a y sub p1 that corresponds to g of t and a y sub p2 that corresponds to h of t, then your overall particular solution is going to be k1 y sub p1 of t plus k2 y sub p of t. So you take whatever linear combination you have of your right-hand side functions if you already have particular solutions. If you don't, then you can just lump everything together. All of these different forms that you have, you can lump them together and do the method of undetermined coefficients in one time. Okay? So the last page of this unit is going through a bunch of problems, but I promise you they won't be very long, because all it's asking for is determining what a good form would be. Now the form is y sub p just in terms of the undetermined coefficients. So we're not actually determining what a, b, c, and so on are. We are just writing out what we think would be a good guess. Now in order to do that, we do have to find the homogeneous solution, because we have to figure out if we need to multiply by a t or t squared or something like that. So we are going to first solve the homogeneous equation, and if you notice, this left-hand side is used in a lot of these problems. So we will find the homogeneous solution once and then be able to reuse it. Okay, so the left-hand side leads to a characteristic equation of r squared minus 3r minus 4, and we're going to set that equal to 0. If we factor this, we'll get an r minus 4 and an r plus 1. So that gives us r equaling 4, r equaling negative 1, which leads to a homogeneous solution of c1 e to the 4t plus c2 e to the negative t. So we need to watch out for either e to the 4t or e to the negative t in the right-hand side. Well, for this one, our right-hand side is just a polynomial, doesn't involve any exponentials. So we don't have anything repeated. So we can just simply write out a polynomial with some undetermined coefficients. We are going to go up to power of 2 and all the way down to just constant values. So we will pick up what would match up with that negative 1 as well. So we're going to have an a t squared. Oops, let me write this. Y sub p of t the form would be a times t squared plus b times t plus c, and that is all we need for part A. For part B, we do have the same left-hand side, so we're going to have the same general solution to the homogeneous. So we need to pay attention to whether our right-hand side involves either e to the 4t or e to the negative t, and it does not. It involves e to the t, but e to the t being multiplied by cosine of 2t, plus that's a different value in the exponent there than the 4 and the negative 1. Even if it had a negative 1 here, it still wouldn't be the same because it's being multiplied by cosine of 2t. Okay? So, with this on our right-hand side, we do need to have an exponential function with the same power in the numerator, and we need to multiply by a cosine and a sine, and each one of those terms is going to have an undetermined coefficient. So it's going to look like this: e to the t times a cosine of 2t plus b sine of 2t. Part C, we again have the same left-hand side, so still paying attention to those two. On our right-hand side, we have 5t squared e to the t. E to the t does not correspond to either one of those, so we can pick our form to have that exponential function, and then we're going to need to multiply by a polynomial of degree 2, counting all the way down to 1. So we're going to have at squared plus bt plus c, and that is what our form is going to be. Now, some of you may be wondering, well, why don't we have another coefficient, let's say, out here? Because that's a function, maybe there's a coefficient there, and there's also coefficients here. You could write an undetermined coefficient out there, but it's actually more than you need, because if you were to distribute this, you would get d times a e to the t squared plus d times b e to the t plus d times c e to the t. And notice these undetermined coefficients can simply be combined. Okay, so although you can write a d there, you don't need to, and it makes it more complicated than it needs to be. So the recommendation is to not include that and just have what is written in green. However, if you were working through a problem like this and you wrote a d there or some other letter for an undetermined coefficients, I would not mark off because mathematically it's equivalent. It's just a little more complicated than what's really necessary. So keep that in mind when you're coming up with your form. If you're talking about multiplication, as long as there is an undetermined coefficient with each one of the terms that's being added or subtracted, you don't need to do it with a term that is multiplying all of the pieces. Okay? All right, part D. We have the same left-hand side, so we're still looking out for e to the 4t and e to the negative t. We now have an even more complicated right-hand side, which is t cubed, e to the negative t, cosine of 3t. So let's deal with e to the negative t, cosine of 3t. And notice we do have an e to the negative t, which is almost, or it is one of the solutions for our homogeneous equation, but it's e to the negative t times the cosine of 3t. And we don't have that as a solution to our homogeneous. So these two things are not the same because they're being multiplied by cosine of 3t. So dealing with the e to the negative t cosine of 3t, we would have an e to the negative t and then multiplying, like what we saw up in part B, a cosine of now 3t plus b sine of 3t, and as we saw in part C, we do not need to multiply by a constant out here because we have the constants here and the exponential multiplies both of those. So this part takes care of what I underlined in yellow there, but we still have to deal with the t cubed part. And since t cubed is multiplying all of this stuff, we are going to need to multiply all of this stuff by a polynomial starting at a general polynomial of degree 3. So that means a t cubed plus b t squared plus c t plus d. But now the issue is I have repeated the usage of a and b. So I could either change the a and b here, or I could change the a and b here. Since I am, sorry about that, since I'm writing it in this order, I'm going to go ahead and change, oops, if my eraser will work. No, apparently not. There we go. I'm going to change those to, I'm going to do F and G. I skipped over E simply because I already had an E here. You could use E as an undetermined coefficient if you want, but you don't have to. And just to make it easier if you were to read this out loud, we only have one E in there. Okay, so the particular here is AT cubed plus BT squared plus CT plus D e to the negative t times F cosine of 3t plus G sine of 3t. All right, that whole thing. Okay, for part E, we have the same left-hand side again, and our right-hand side is pretty complicated. So let's just take it piece by piece and see where we go. Since we have the same left-hand side, we need to pay attention to the same two exponential functions, e to the 4t and e to the negative t. E to the 2t is neither one of those. So for that piece, we are simply going to have a e to the 2t. For 2 sine of t, that does not correspond to either of our homogeneous solutions. So we do need to remember to have a sine of t and a cosine of t. Oops, I need to change my letter there. So b sine of t and c cosine of t. Then we have e to the t cosine of 2t. That does not correspond to the homogeneous solution either. Again, we need to remember to have a cosine and a sine function. So we will have e to the t. And you know what? I'll go ahead and write it this way. D e to the t cosine of 2t plus, I'm going to skip e again, so f e to the t sine of 2t. And notice you could have also written it with the e to the t factored out, but you would need an undetermined coefficient with cosine and another one with sine. And then we have our t squared term, and we need to remember that we have to have a polynomial of degree 2 with all of the terms there. So we will have a g t squared plus h t, and I'll skip I as well. Well, we can write I. I was thinking we already had it in the problem, but we don't. Plus I. And there we go. That is the form of our particular solution. Now, before you start getting really worried, I do want to assure you that you will not see either the form in part D or the form in part E where you actually have to come up with the undetermined coefficients. I might give you something. I'll definitely give you things that have 2 unknowns. I may also give you something with 3 unknowns, as long as it is not a very complicated situation. Like this sort of thing wouldn't be too hard to differentiate, although the e to the t does make it a little bit harder. Something like this would definitely be doable because the derivatives are very easy to obtain. Okay, so if I'm asking you to find the values of the undetermined coefficients, I won't give you anything larger than 3 undetermined coefficients. If I'm just asking you to find the form, then I may give you something very complicated like this, but you don't have to find the values of your undetermined coefficients. Okay, for our last problem, notice we do have a different left-hand side. So let's go ahead and solve that homogeneous problem. It will give us an r squared minus 6r plus 9 equals 0. And if we factor that, we have an r minus 3 squared equaling 0. So r equals 3, and this leads to a homogeneous solution of c1 e to the 3t plus c2t e to the 3t. And notice our right-hand side does correspond to that, and it's a repeated root. So this is that one rare case when we have to remember to multiply our particular form by a t squared, because we have already used up the t times e to the 3 option. So y sub p of t will equal a t squared e to the 3t. In this case, you do not need to have a t squared and a t to the first and a t to the 0, because we don't have a polynomial on our right-hand side. We're simply multiplying by t squared so that this equation, this function, is distinct from the two functions that we have in the homogeneous solution. However, if you did, okay, I wanted to write in a different color, but it's not quite working right now. There we go. If instead you said at squared plus bt plus c times e to the 3t, that would still technically be correct, but it's kind of like what I was talking about up here in part D, in that it's more complicated than what you need. This piece, the bt times e to the 3t, and this piece, the c times e to the 3t, those two terms are both going to end up disappearing when you substitute them into the left-hand side. They'll both go to 0. So it's not helpful, and you should end up getting something that doesn't tell you what b and c need to be. In other words, b and c can essentially be anything, and it's still satisfied. So that makes it a lot more complicated than necessary, but it is technically correct. Okay, so if you did write it that way, you would get credit for it. But just keep in mind that it's more complicated than it needs to be. So that does wrap up our Unit 13 material. So I will end the video here. As always, if you have any questions, feel free to ask.